So, today I will discuss sheafification of a pre-sheaf. First, recall the definition. Recall that say X be a topological space, and F say a pre-sheaf on X. Then there exists a sheaf on X, sheaf F plus say on X, and a morphism theta say from F to F plus satisfying the following universal property. For any sheaf G on X and any morphism say phi from F to G, there exists a unique morphism psi from F plus to G such that the psi composition theta is equals to phi. It means this diagram, this F to G we have a map and F to F plus we have a map. This is theta, this is phi. So, there exists a unique morphism from F plus to G, unique, say psi, such that this diagram commutes. So, this is how we define the sheafification of a pre-sheaf, right. Then F plus is called the sheafification. The sheafification of F. Okay. Now, I will show that there such sheafification of a pre-sheaf exists, okay, and it will be unique. It follows from the universal property, okay. Existence. For that, I will introduce the concept of Etale space of a pre-sheaf, okay. Now, existence. Again, consider that X a topological space, and F a pre-sheaf on X. Then we define Etale space as the disjoint union of each stocks at P, where P is inside X, the stock of F at P for each point P inside X, okay. So, this disjoint union, this is called Etale space. Etale space, okay. Right now this is a set, but we will give a topology in that space, in this space, okay. Now, consider this map pi say from this Etale space of F to X, where each S inside Fp, this goes to the point P. This is called projection map. projection map. Okay. Now, for any open subset U of X and for any section inside f of U, consider the map, say S bar, from U to this Etale space of F, where each point P inside U, this goes to SP. This is the actually the germ of S at P. So it is nothing but Fu to Fp. We already know we have a map, right? Fu to Fp for P inside U. So S goes to Sp. So this is a germ. This Sp is a germ of S at P. So interesting thing happens that we notice that pi composition, this S bar, this is identity from U to U. Okay. So S bar is a section. This term, this is a new term. So this is a section of pi over U. Now, given okay. Now give this this Etale space the strongest topology. The strongest topology I will explain in a minute. The strongest topology such that for every open subset inside U inside X and every section inside f of U, this map S bar from U to this Etale space of F is continuous. Now, what does it mean by the strongest topology? The strongest topology means that any subset inside any subset inside this Etale space is open if and only if its means for each S bar its inverse image will be open. So so any subset, a subset inside this Etale space, this is open if and only if its inverse image under this all S bar are open. So that's what I mean by the strongest topology. Okay. Now, for any open set inside X, open set U inside X, we define F plus U to be the set of all continuous sections of pi over U. This means this T, suppose a section, it means a section T means this is a map from U to this this Etale space of F T, such that it's when we compose it with this say pi, here to X we have a pi, right. So, when we compose it, this will be pi compose T, this will be identity on U. So, we consider all such sections from U to this Etale space of F, all continuous sections. Okay. Now, claim that F is a sheaf on X. This is easy verifications, I will not do it. I will leave this for you to verify, left as an exercise. Okay. Now, we have a map from F to F plus theta. We have a natural map. What? That F u for any open set, say U for open set U inside X, we have F u to F plus u. We have a natural map, right, where this any section inside F of u, this goes to S bar. This is a section in F plus u. So, this is, you can say that this is theta u. Okay. So, this is a sheaf. Now, we want to show that this F plus is actually the sheafification of F. So, for that we have to show the universal property, right. So, what we have to show is that F to G, if we have a map for any map from F to G where G is a sheaf, and F to F plus we already have a map, this theta, we have to show that there exists a unique psi, we have to show. So, this is what we have to show. So, this in turn we have to show that for any open set U inside X, we have to show that F of u to if we have a map from F of u to G of u, say this is phi of phi u. So, this is theta u, it goes to F plus u. So, we have to construct a map from F plus u to G of u. We have to construct such a map such that this diagram commutes. So, construct psi u. So, this is what we want to do. Now, say T is a section, say from F plus u. So, T means T is a map from u to this Etale space of F, where suppose if each point goes to T of P, right. Now, okay. Now, this T of P, because it is a section, now section means here to here, if I have a map, say this is T from here to here. So, it is a section, it means that here to if I have X, this pi, this goes to also, this is identity. So, this goes to P, right. So, this means that this T of P, this is actually inside Fp, right. This is a this is inside Fp. So, my claim is that for every P inside this U, there exists a there exists a UP, a open subset inside U containing P, and S inside F of UP, a section inside F of UP, such that this T of Q is equals to S is equals to SQ for all Q inside UP. So, this SQ is nothing but a germ at the point Q. Okay. So, this means that this T restricted to this UP, this will be equals to this S bar, the S bar means whatever notation we have used here, right. So, this thing follows. I am also not going to prove this. So, this will means I will give you hint. This will follow from the the topology of this Etale space. The topology is the strongest topology, right, such that the sections are continuous. So, it will follow from the if you if you verify in details that what are the open sets in this topology, in the strongest topology, using that you can if you observe those things, then you can prove this claim. Okay. I will also leave this as an exercise, left as an exercise. So, therefore, we have using this claim says that therefore, we have a open covering of U, open covering, and we have some section inside F of ui, Si inside F of ui, such that this T restricted to ui, this is nothing but equals to Si bar. So, this is the claim says means from the claim it follows. Okay. Now, it says that this Si bar, when we restrict to this ui intersection uj, this will be same as Sj bar restricted to ui intersection uj. Okay. So, fine. Now, we want to give a map from F plus to G, right, or F plus u to Gu. So, we want a map from F plus u to Gu. So, for that we have T, this for this T has to go to somewhere inside Gu, right. So, here for this T we have this Si bars, some Si we have, some ui Si, means we have some open covering of U, which is union ui, and we have some Si's inside F of ui. Okay. Now, using these Si's we will define the map, define the means wherever the T will go inside Gu. Okay. Now, look, F of ui to G of ui, we have this phi of phi ui, where Si goes to this phi ui Si. Okay. Right. Now, okay. Okay. Now, for all points q inside this ui intersection uj, we see that that this s bar si bar restricted to ui intersection uj is equals to sj bar restricted to ui intersection uj. So, it says that si bar q, this is equals to sj bar q, right. Now, this is nothing but si the germ of si at q, and this is nothing but germ of sj at q. So, these are same, right. Now, this says that si restricted to ui intersection uj minus this sj restricted to ui intersection uj, this section, if I take germ at q, this will be equals to 0. Okay. Now, we want to apply this now we want to apply this phi of ui or phi of uj. Okay. Phi of ui or phi of uj. So, it says that phi of ui, phi ui si, this restricted to ui intersection uj minus this phi of uj, we apply to sj, this restricted to ui intersection uj. If I take its germ, then it will be equals to 0. Now, this phi ui si restricted to ui intersection uj minus phi uj sj restricted to ui intersection uj, this is inside g of ui intersection uj. Now, g is a sheaf. Now, g is a sheaf. Now, I will use a result for a sheaf say f and on x and s inside fu for some open subset inside x, sp equals to 0 for all p inside u, implies that s equals to 0. So, this is very easy to prove. Okay, you have to use the sheaf property to show that this s is actually equals to 0. If all the stocks means all the germs is equals to 0, then the section has to be 0. So, using that, here we already have that this this section is germ at q for each q inside ui intersection uj is 0. So, this has to be 0. So, it means that phi ui si restricted to ui intersection uj, this is equals to phi uj sj restricted to ui intersection uj. Okay. So, now we can use the sheaf property. Okay. So, there exists a R inside GU such that R restricted to this uy, this will be equals to phi uy si. Okay. Now we define this map f plus u to gu, we define this map t goes to r, define. Now other things are means easy to verify, that this means means if we define this map, this psi u like that, then it will satisfy the means it will commute with the diagram, the diagram will commute. And for the uniqueness, this follows from the construction, of psi. Uniqueness follows from the construction. You can means easily verify these things. So you have to just observe properly. Okay, let me stop here. Thank you.